Close your eyes. Now imagine nothing. Not darkness, not emptiness. Imagine a state of absolute nothing. No time, no space, no matter, no energy. Nothing. Now imagine that nothing becoming everything. How does that happen? How did we get here? Where did it all come from? These are questions that have haunted humanity since we first looked up at the stars. Questions that philosophers have debated for thousands of years. Questions that scientists have been trying to answer for centuries. And today, in 2026, we are closer than ever to understanding the answers. But what we're discovering is far stranger, far more terrifying, and far more beautiful than anyone ever imagined. This is the story of the universe. Not just the facts you've heard before, not just the basic science. We're going to take you on a journey that will fundamentally change how you see existence itself. From the very first moment of creation, through the violent birth of stars, to the mind-bending reality of black holes and dark matter, to the ultimate fate of everything we know. This is Focusmint, and this is the complete story of the universe. A story that starts with a question we've been asking for millennia. Where did everything come from? By the end, you'll understand the universe like never before. You'll know things most people will never learn, and you'll never look at the night sky the same way again. Are you ready? Let's begin. It starts with a question, a simple question. Where did everything come from? For most of human history, the answer was simple. God created the universe. And in many ways, that's still the answer billions of people believe today. But over the past century, science has presented a different story. A story that sounds like science fiction, but is backed by more evidence than almost any theory in human history. This is the story of the Big Bang. The Big Bang theory didn't start with scientists. It started with an astronomer named George Lemaitre, a Catholic priest and physicist, who proposed in 1927 that the universe began with a primordial atom, a single point of infinite density that exploded outward, creating space and time itself. At first, even other scientists laughed at the idea, but then, in 1964, something happened that would change everything. Two radio astronomers named Arno Penzias and Robert Wilson discovered something they couldn't explain. They kept hearing static noise in their antenna. No matter where they pointed it, no matter what they tried, the static wouldn't go away. That static noise was the cosmic microwave background radiation, the residual heat from the initial explosion of creation. It was the smoking gun for the Big Bang theory. The universe was once incredibly hot and dense, and as it expanded, it cooled. That cooling left behind a background radiation that's present everywhere in the universe. This discovery won Penzias and Wilson the Nobel Prize in Physics in 1978. And it confirmed what Lemaitre had suspected. The universe had a beginning. But here's what most documentaries don't tell you. The Big Bang wasn't an explosion. That's a common misconception. It was something far more strange. In the first fraction of a second after creation, the universe underwent a process called inflation. It expanded faster than the speed of light. In less time than it takes you to blink, the universe grew from something smaller than an atom to something larger than the observable universe. This isn't my opinion. This isn't speculation. This is what the mathematics tells us, and what the evidence confirms. Within the first 3 minutes of creation, something remarkable happened. The universe had cooled enough for the fundamental forces to separate. Gravity became its own force. The strong nuclear force held protons and neutrons together, and the lightest elements began to form. Hydrogen, helium, traces of lithium. This was the universe's first chemistry. Before this moment, the universe was too hot for atoms to exist, too energetic. But when it cooled enough, electrons finally orbited nuclei, and the first true atoms were born. Then came the Dark Ages. For millions of years after the Big Bang, the universe was dark. No stars, no galaxies, just a vast sea of primordial gas slowly expanding, slowly cooling, slowly gathering under the influence of gravity. This is one of the least discussed periods in cosmic history, and it's fascinating. We live in a universe that was born in light, then fell into darkness, and only emerged back into light when gravity finally won its battle against expansion. The first stars were unlike anything in our universe today. They were massive, incredibly massive, hundreds of times the mass of our sun, and they burned blue and hot, producing intense radiation that would eventually ionize the surrounding gas and end the Dark Ages forever. These first stars lived fast and died young, some lasting only a few million years before exploding as supernovae. But in that brief existence, they created the heavier elements: carbon, oxygen, iron, everything that would eventually become you and me. But here's what the textbooks don't emphasize enough. The first stars didn't form in isolation. They formed along a cosmic web, a structure of dark matter that spanned the entire universe. Dark matter is one of the greatest mysteries in modern physics. We can't see it, we can't detect it directly, but we know it exists because of its gravitational effects. Without dark matter, galaxies wouldn't form, stars wouldn't form, nothing would form. And yet, 85% of the matter in the universe is dark matter. The first stars gathered into clusters. The clusters gathered into galaxies. Gravity worked at every level, building structures from the smallest to the largest. Our own Milky Way galaxy formed around 12 billion years ago, and it's been growing ever since. But galaxies aren't just collections of stars. They're dynamic ecosystems. They merge with other galaxies. They consume smaller galaxies. They undergo bursts of star formation that can last millions of years, and they're home to phenomena that still puzzle scientists today. Every large galaxy has a supermassive black hole at its center. This is one of the most shocking discoveries in modern astronomy. Our Milky Way has one. Andromeda has one. Every spiral galaxy we've observed has one. These black holes can be billions of times the mass of our sun, and they're not just passive consumers. Many of them shoot out jets of energy that extend for millions of light years. The energy output from these jets can exceed the energy output of entire galaxies, and we're still not entirely sure how they form. Some black holes are what's called active. They feed on the gas and stars around them, creating what's called an active galactic nucleus, or AGN. The most luminous AGNs are called quasars, and they're the most distant objects we can observe. Some quasars date from when the universe was less than 1 billion years old. That's a problem. How do you form a billion solar mass black hole in less than 1 billion years? That's like building a mountain the size of Everest in less than a day. It shouldn't be possible, and yet it happened. But perhaps the strangest discovery in cosmology wasn't in the distant past. It was in 1998, when astronomers discovered that the universe's expansion is accelerating, not slowing down, accelerating. This was completely unexpected. The discovery earned a Nobel Prize in 2011, and it led to one of the greatest mysteries in science: dark energy. Dark energy is a property of space itself. It causes the fabric of space to expand faster and faster. In the future, distant galaxies will be moving away from us faster than light. They'll disappear from our view forever. The universe is becoming a darker, colder, emptier place, and it's accelerating toward that fate. Before we go further, we need to understand something fundamental about the universe. The universe is finite in age. It's about 13.8 billion years old, and light travels at a finite speed. This means we can only see objects whose light has had time to reach us since the beginning of the universe. This defines the observable universe, a bubble of space about 93 billion light-years in diameter, with us at the center. But here's the thing. The observable universe is probably just a tiny fraction of the total universe. What lies beyond the edge of what we can see? We have no idea, and we can never know. The edge of the observable universe isn't a wall, it's a horizon we can never cross. Some physicists believe that our universe isn't the only universe. They believe in what's called the multiverse, an infinite collection of universes, each with different physical laws, different constants, different histories. Some of these universes might be identical to ours. Some might be radically different, where gravity works differently, where atoms don't exist, where life is impossible. In some versions of this theory, new universes are constantly being created, spawning off from our own, in a process called eternal inflation. This isn't science fiction. This is mainstream theoretical physics, and it might be true. But here's what's really strange. The universe appears to be fine-tuned for life. If the gravitational constant were slightly different, stars wouldn't form. If the strong nuclear force were slightly weaker, atoms wouldn't exist. If the expansion rate of the early universe were slightly different, all matter would have either collapsed back into a singularity, or flown apart too quickly to form structures. The universe we see appears to be incredibly unlikely, and yet here we are, asking questions about it. This is called the fine-tuning problem, and it's one of the most profound puzzles in science and philosophy. So where did everything come from? The evidence points to a hot, dense beginning about 13.8 billion years ago. But what caused that beginning? What existed before? Why is there something rather than nothing? These questions remain unanswered, and perhaps they'll remain unanswered forever. But as we continue our journey through space and time, we'll encounter phenomena that push the boundaries of what we thought was possible. Phenomena that challenge everything we know about the nature of reality. If the universe is a cosmic ocean, then stars are its living creatures. They are born, they live, they die, and in their deaths they create the conditions for new births. This is the cycle of stellar existence, and it is perhaps the most beautiful, most violent, and most important process in the universe. Without stars, there would be no planets, no life, no us. Everything that makes you, me, and every other thing you see around you was forged in the heart of a dying star. This is not poetry. This is astrophysics. Stars begin their lives in stellar nurseries. These are regions of space where gas and dust are slightly denser than their surroundings. Over millions of years, gravity pulls these particles together. The cloud grows more massive, it grows hotter, and eventually, at its core, the temperature and pressure become so extreme that nuclear fusion begins. Hydrogen atoms fuse into helium, releasing enormous amounts of energy, and a star is born. This process takes about 50 million years for stars like our Sun. For massive stars, it happens much faster. Once a star begins fusing hydrogen, it enters what's called the main sequence. This is the longest phase of a star's life, where it steadily burns hydrogen and maintains a balance between gravity pulling in and radiation pressure pushing out. Our Sun is a main sequence star. It's been burning hydrogen for 4.6 billion years, and it will continue for another 5 billion years. But not all stars are the same. Some are red dwarfs, small and cool, barely larger than Jupiter. They burn their hydrogen so slowly that they can live for trillions of years, longer than the current age of the universe. Others are blue giants, massive and hot, burning through their fuel in just a few million years. If you plot all the stars on a diagram of their temperature versus their luminosity, you get what's called the Hertzsprung-Russell diagram, and it's one of the most important tools in astronomy. Most stars fall along a diagonal line called the main sequence, but there are also stars above the main sequence, giant stars that are cool but incredibly luminous. And there are stars below it, white dwarfs that are hot but dim. These are the remnants of stars that have died, and the path a star takes across this diagram tells the story of its life and death. When a star like our Sun runs out of hydrogen to fuse, it doesn't simply fade away. It undergoes a dramatic transformation. The core collapses, heating up until helium fusion begins. This creates a massive release of energy that causes the star's outer layers to expand. The star becomes a red giant. For our Sun, this will happen in about 5 billion years, and when it does, Mercury and Venus will be consumed. The Sun will expand to encompass the orbit of Earth, our planet will be inside the sun, and all life on Earth will end. But this is only the beginning of the end. When the sun finally runs out of helium, it will begin to shed its outer layers. These layers will expand outward, creating a beautiful shell of gas called a planetary nebula. Don't let the name fool you. Planetary nebulae have nothing to do with planets. They're named because early astronomers thought they looked like planets through small telescopes. These nebulae are the final breaths of stars like our sun, and they're some of the most beautiful objects in the universe. After the outer layers are expelled, what's left is the core, a white dwarf. This is an object about the size of Earth, but with the mass of a star. A teaspoon of white dwarf material would weigh about as much as a car. White dwarfs are incredibly dense, composed almost entirely of degenerate matter, a state of matter where electrons are packed so closely together that quantum mechanics takes over. These objects cool slowly over billions of years, eventually fading into darkness, and that will be the fate of our sun. But not all stars meet such quiet ends. The most massive stars live fast and die young, and their deaths are the most violent events in the universe since the Big Bang itself. Let's see what happens when a star dies. When a star more than about 8 times the mass of our sun runs out of fuel, something dramatic happens. The core collapses. In less than a second, the core shrinks from the size of the sun to the size of a city. The outer layers fall inward and then slam into the rigid core, rebounding in the most violent explosion in the universe. This is a supernova. The explosion releases more energy than our sun will produce in its entire lifetime. In a few seconds, a supernova can outshine an entire galaxy of 100 billion stars. The most famous supernova remnant is the Crab Nebula. In 1054 AD, Chinese astronomers recorded a new star in the sky. It was so bright, it was visible during the day for 3 weeks. That new star was a supernova explosion, and the expanding debris from that explosion is still moving outward today, creating the beautiful nebula we can observe with telescopes. Supernova remnants are cosmic recycling centers. The material expelled in these explosions goes on to form new stars, new planets, new everything. But what happens to the core after a supernova? It depends on the mass. For stars between 8 and about 20 solar masses, the core becomes a neutron star. This is an object with the mass of a star compressed into the size of a city. A neutron star is so dense that if you dropped something on it from just a meter above, it would hit the surface at millions of kilometers per hour. The energy of impact would be like a nuclear explosion. Neutron stars spin rapidly, sometimes hundreds of times per second, and they have magnetic fields trillions of times stronger than Earth's. Many neutron stars are also pulsars. These are neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a cosmic lighthouse. If Earth happens to be in the path of one of these beams, we see regular pulses of radiation, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, a graduate student who was dismissed by her advisor as "little green men" before the pulsar theory was accepted. She should have won the Nobel Prize for that discovery. But her achievement is no less remarkable. For the most massive stars, even neutron stars aren't dense enough. When the core of a supermassive star collapses, it keeps collapsing past the neutron star stage, past anything we've ever observed directly. And eventually, it collapses into a singularity, a point of infinite density surrounded by an event horizon. This is a black hole. Even light cannot escape from within the event horizon. Nothing can. The star has died in the most extreme way possible, and what remains is one of the most mysterious objects in the universe. The event horizon of a black hole isn't a physical surface, it's a boundary in spacetime, a point of no return. Once you cross the event horizon, there's no turning back. The gravitational pull is so strong that to escape, you'd have to travel faster than light, and that's impossible. Time itself behaves differently near a black hole. If you watch someone fall into a black hole from a distance, you'd see them slow down and freeze at the event horizon, their image fading away over time. But to the person falling in, time would feel normal. They'd cross the event horizon without even noticing. This is the nature of spacetime near a black hole. It's not a wall, it's a horizon. Most black holes we observe aren't isolated. They're surrounded by accretion disks, swirling disks of gas and dust being pulled inward. As this material falls toward the black hole, it heats up to millions of degrees. It emits X-rays and other radiation that we can detect with telescopes. This is how we find black holes. We can't see the black holes themselves, but we can see the superheated matter orbiting them. And in some cases, we can measure the mass of the black hole by watching how the matter moves. In 2019, humanity achieved something remarkable. We took the first direct image of a black hole. Using a network of radio telescopes spanning the entire Earth, astronomers captured an image of the black hole at the center of galaxy M87. It showed a bright ring of emission surrounding a dark center, the shadow of the black hole against the glowing accretion disk. This image won the Nobel Prize in Physics in 2020, and it confirmed what Einstein's theory of general relativity predicted over a century ago. Black holes are real, and they're stranger than we imagined. There are different types of black holes. Stellar mass black holes form from the collapsed cores of massive stars. They typically have masses between 3 and 100 solar masses. Supermassive black holes are found at the centers of galaxies. They have masses between millions and billions of solar masses. And then there are intermediate mass black holes, whose existence is still being debated. How do supermassive black holes form? We don't know for certain. Maybe they grow by consuming stars and gas over billions of years. Maybe they formed from the merger of many stellar mass black holes. Or maybe they formed directly from the collapse of massive gas clouds in the early universe. This is an active area of research, and the answer might surprise us. Stars are born, live, and die. In their deaths, they create the elements necessary for life. They seed the universe with complexity. But stars are only part of the story. They exist within galaxies, vast systems of stars, gas, dust, and dark matter. And galaxies are organized into even larger structures. Let's take a look at the cosmic web that connects everything in the universe. When you look at the night sky, those thousands of stars you see are just a tiny fraction of what's in our Milky Way galaxy. Our galaxy contains between 100 and 400 billion stars, and there are billions of galaxies in the observable universe, each containing billions of stars. Galaxies come in different shapes and sizes. Spiral galaxies like our Milky Way have rotating arms of stars and gas. Elliptical galaxies are smooth, football-shaped collections of mostly old stars. Irregular galaxies have no defined shape, and dwarf galaxies are small, containing just a few billion stars. Each type tells a different story of formation and evolution. Our home galaxy, the Milky Way, is a spiral galaxy with 4 major arms. We're located in a minor arm called the Orion Arm, about 26,000 light-years from the center. The galaxy is about 100,000 light-years in diameter, and at its center lies a supermassive black hole called Sagittarius A star. This black hole has a mass of about 4 million solar masses, and it's currently dormant, having run out of matter to consume. But that wasn't always the case. In the past, our galaxy was an active galaxy, shooting out jets of energy that extended for thousands of light years. Galaxies don't exist in isolation. They interact, they merge. Over the course of billions of years, gravity brings them together. When 2 spiral galaxies collide, they merge into an elliptical galaxy. The spiral arms are disrupted. The gas clouds are compressed, triggering bursts of new star formation. And eventually, the central black holes merge as well. Our Milky Way is heading for a collision with the Andromeda Galaxy in about 4.5 billion years. But don't worry, by then, our sun will have died, and Earth will be long gone. When we look at the universe on the largest scales, we see a structure that's both beautiful and terrifying. The universe is not uniform. It's organized into a cosmic web of filaments and voids. Galaxies cluster along filaments of dark matter, creating long chains that stretch for hundreds of millions of light years. Between these filaments are voids, vast regions of empty space, millions of light years across, with almost no galaxies at all. This structure is the largest pattern in the universe, and it took billions of years to form. In 2000, astronomers completed the Sloan Digital Sky Survey, a massive project that mapped the positions of millions of galaxies. The resulting map looked like a map of the internet, a web of interconnected nodes. But this wasn't a designed system. This was the universe. Gravity had been working for billions of years to create this structure. And when you zoom out, the pattern becomes clear. We live in a cosmic web, and our galaxy is just one node in an infinite network. Galaxies are grouped together into clusters. These clusters can contain anywhere from a few dozen to thousands of galaxies. Our own Milky Way is part of a small group called the Local Group, which contains about 80 galaxies. The nearest major galaxy cluster is the Virgo cluster, about 54 million light-years away. Galaxy clusters are held together by gravity, including the gravity of the dark matter that surrounds them. And between clusters are vast voids. The universe is mostly empty space. Dark matter is the scaffolding on which the cosmic web is built. Without dark matter, gravity would be too weak to pull matter into the filaments and clusters we observe. Dark matter's gravitational effects can be measured through techniques like gravitational lensing, where the gravity of dark matter bends light from distant galaxies. By mapping these bending patterns, astronomers can reconstruct the distribution of dark matter in the universe. And what they find is a cosmic web that's even more extensive than the visible web of galaxies. Among the most distant objects we can observe are quasars. These are supermassive black holes at the centers of galaxies, actively feeding on surrounding matter. As the matter falls into the black hole, it heats up and emits enormous amounts of radiation. Some quasars are so luminous that they outshine their entire host galaxies by a factor of 100. And the most distant quasars date from when the universe was less than 1 billion years old. The James Webb Space Telescope, launched in December 2021, has revolutionized our view of the early universe. It has observed galaxies that formed when the universe was less than 500 million years old. And these galaxies are more massive and more evolved than we expected. They shouldn't exist. According to our models, there wasn't enough time for galaxies to grow so large so quickly. But they do exist, and we're still trying to understand why. Before there were galaxies, there were stars. The very first stars were different from the stars we see today. They were made almost entirely of hydrogen and helium, the elements created in the Big Bang. These are called population 3 stars. They were massive, hot, and short-lived, and they created the first heavier elements. But we've never observed a population 3 star directly. They're too far away and too faint. Everything we know about them comes from computer simulations and theoretical models. The James Webb Space Telescope might be able to see the first generation of galaxies that formed from these early stars, and that will tell us if our models are correct. After the Big Bang, the universe was mostly neutral hydrogen. It wasn't until the first stars and galaxies formed that the hydrogen began to be ionized, stripped of its electrons by the intense radiation from these early light sources. This period is called reionization. It took hundreds of millions of years, and it transformed the universe from a dark neutral place to the ionized, transparent universe we see today. Understanding reionization is one of the key goals of modern cosmology, and the James Webb Space Telescope is our best tool for studying it. In 2003 and 2004, the Hubble Space Telescope stared at a seemingly empty patch of sky for over 1 million seconds. That image became the Hubble Ultra Deep Field. It revealed thousands of galaxies in a patch of sky smaller than your thumbnail held at arm's length. Some of these galaxies are over 13 billion light-years away. Their light has been traveling for 13 billion years to reach us. And in that tiny patch of sky, we're seeing the universe as it was when it was less than 1 billion years old. This is the deepest view of the universe ever achieved, and it's both humbling and awe-inspiring. Galaxies evolve over time. Small, irregular galaxies merge to form larger galaxies. Spiral galaxies merge to form elliptical galaxies. Galaxies that are rich in gas form new stars. Galaxies that are poor in gas become red and dead. This evolution is driven by gravity, by mergers, by feedback from supernovae and black holes, and it's happening all around us, all the time. Our galaxy is in the process of consuming smaller satellite galaxies, and in 4.5 billion years, it will merge with Andromeda. We're part of a small group of galaxies called the Local Group. It includes the Milky Way, Andromeda, and about 80 smaller galaxies. The Local Group is about 10 million light-years across, and it's part of a larger structure called the Local Supercluster, which contains hundreds of galaxy groups and clusters. But superclusters aren't bound by gravity. They're just temporary configurations that will disperse over billions of years. The universe is becoming more uniform, more empty. We're living during a special time when the structure is still visible. In the distant future, the universe will be dark and empty, and any civilization born then will have no idea that galaxies ever existed. This is the fate of our universe. Not a big crunch, not a big rip, a slow, cold fade into darkness. Over trillions of years, stars will burn out, black holes will slowly evaporate, and eventually, the universe will reach a state of maximum entropy, a state of perfect uniformity where nothing interesting ever happens again. This is the ultimate fate of our cosmos. But don't worry, we have trillions of years before that happens. We have right now, and that's what matters. We've covered the birth and death of stars. We've explored the cosmic web that connects galaxies across the universe. But there are objects in the universe that push the boundaries of what we thought was possible. Objects that distort spacetime itself. Objects that shouldn't exist according to everything we know. These are black holes, and we're only beginning to understand them. Black holes are the most extreme objects in the universe. They're places where gravity has won its battle against all other forces, where spacetime is so curved that nothing can escape, where the laws of physics as we know them break down. Understanding black holes requires us to push the limits of general relativity, quantum mechanics, and thermodynamics. And yet, black holes are everywhere. Every large galaxy has one. Some stellar mass black holes are created when massive stars die, and the most massive black holes in the universe are billions of times the mass of our Sun. Black holes are direct consequences of Einstein's theory of general relativity. In this theory, gravity isn't a force. It's the curvature of spacetime caused by mass. The more mass, the more curvature. A black hole is what happens when the curvature becomes so extreme that spacetime closes in on itself. There's a boundary called the event horizon, beyond which spacetime curves so much that all possible paths lead inward. It's not that you can't escape because the gravity is too strong. It's that escape requires moving in a direction that doesn't exist anymore. Time behaves differently near black holes. Due to gravitational time dilation, time runs slower in stronger gravitational fields. If you watch someone fall toward a black hole, you'd see their clock tick slower and slower as they approach the event horizon. They'd never quite reach it, from your perspective. But to them, time would feel normal. They'd cross the event horizon without even noticing, then be stretched and spaghettified by the intense tidal forces within. This is the fate awaiting anyone who falls into a black hole. Not a quick death, a slow, inevitable dissolution. Black holes aren't completely black. According to quantum mechanics, virtual particles are constantly being created and destroyed everywhere in space. Normally, these pairs of particles and antiparticles annihilate almost instantly. But near the event horizon, one particle can fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This is Hawking radiation, named after physicist Stephen Hawking, who discovered this theoretical effect in 1974. And it means black holes aren't eternal. They slowly evaporate. The smaller the black hole, the more Hawking radiation it emits. A black hole with the mass of our Sun would take about 10 to the power of 67 years to evaporate completely. That's far longer than the age of the universe. But a primordial black hole, if it exists, could be evaporating right now. And if we could observe one, we'd see it explode in a burst of gamma rays. So far, we haven't detected any such explosions. But the search continues. Eventually, all black holes will evaporate. And when the last black hole disappears, Hawking radiation will be the only emission in the universe. And then, even that will fade. One of the biggest unsolved problems in physics is the black hole information paradox. Quantum mechanics tells us that information is never destroyed. If you burn a book, the information in that book isn't gone. It's encoded in the smoke and ashes and heat. It's just scrambled beyond recovery. But, if you throw information into a black hole, what happens? The black hole evaporates. And when it's gone, where does the information go? According to quantum mechanics, it should still exist somehow. But general relativity seems to say it disappears. This contradiction is at the heart of modern theoretical physics, and we're still working to resolve it. The most massive black holes are found at the centers of galaxies. Our galaxy has one with a mass of about 4 million solar masses. The largest known black hole, in the galaxy NGC 4089, has a mass of about 21 billion solar masses. These supermassive black holes can have profound effects on their host galaxies. When they're actively feeding, they create active galactic nuclei, which can outshine the entire galaxy. They shoot out jets that extend for millions of light years, and they're probably responsible for quenching star formation in massive galaxies. Why do massive elliptical galaxies have so few young stars? Why are they mostly red and dead? The answer seems to be supermassive black holes. When a black hole is actively feeding, the released energy heats up or expels the surrounding gas. And without gas, no new stars can form. This process is called feedback, and it's one of the key mechanisms for understanding galaxy evolution. Without black holes, the universe would look very different. There would be many more giant elliptical galaxies, and the night sky would be much brighter. Stellar mass black holes have masses between 3 and 100 solar masses. Supermassive black holes have masses between millions and billions of solar masses. Is there something in between? That's the question behind intermediate mass black holes. We found a few candidates, but we're not sure. Intermediate mass black holes might form from the merger of stellar mass black holes or from the direct collapse of gas clouds. Finding them is difficult because they're smaller and harder to detect than their supermassive cousins. Black holes can form from stellar collapse. But maybe black holes formed before stars existed. In the very early universe, density fluctuations might have been strong enough to create black holes directly, without the need for stellar evolution. These are primordial black holes. They could have any mass, from tiny to huge. And some theories suggest that primordial black holes could explain dark matter. If primordial black holes exist in sufficient numbers, they could account for the gravitational effects we attribute to dark matter. This is an active area of research, and it's one of the few scenarios where dark matter might be explained by a single, known type of object. Black holes raise the possibility of other exotic objects. Wormholes, for example, are theoretical tunnels through spacetime. They could connect two distant points in space, or two distant moments in time. Some solutions to Einstein's equations describe wormholes, but these solutions require exotic matter, matter with negative energy density, which may not exist in our universe. And even if wormholes existed, they'd be incredibly unstable. The slightest perturbation would cause them to collapse. So don't count on using wormholes to travel to distant stars. They're probably science fiction. Black holes raise the possibility of time travel. Some solutions to Einstein's equations describe orbits that return to the past. In a rotating black hole, there might be regions where the rotation is so fast that frame dragging creates closed time-like curves. This would allow you to return to before you left. But this violates our intuition about causality, and it raises paradoxes. What if you traveled back in time and killed your grandfather? These paradoxes suggest that closed time-like curves might be forbidden by some as-yet unknown law of physics. The universe doesn't like paradoxes. In 2015, something remarkable happened. For the first time, we directly detected gravitational waves, ripples in spacetime caused by violent events in the universe. The source was two black holes, each about 30 solar masses, merging about 1.3 billion light-years away. The merger released more energy than the combined output of all the stars in the observable universe. This detection earned a Nobel Prize in Physics in 2017. And it opened a new window on the universe. We can now hear black holes colliding. We can measure their masses and spins, and we can test general relativity in the most extreme environments ever observed. Gravitational waves are detected by interferometers, massive instruments that measure tiny changes in distance. LIGO, the Laser Interferometer Gravitational Wave Observatory, consists of 2 detectors in the United States. Virgo is in Italy, and CAGRA is in Japan. These detectors can measure distance changes smaller than 1,000th the diameter of a proton. That's incredibly precise, and they've detected dozens of black hole mergers and neutron star mergers. Each detection tells us something new about these extreme objects. We're entering an era of gravitational wave astronomy, and the universe has never sounded more interesting. Future detectors like LISA, the Laser Interferometer Space Antenna, will be sensitive to gravitational waves at different frequencies. This will allow us to detect supermassive black hole mergers, which LIGO and Virgo can't see. It will allow us to study the behavior of matter near black holes, and it will test general relativity in regimes we've never been able to probe. We're living in a golden age of black hole research, and the discoveries are coming faster than ever. We've explored the life and death of stars. We've mapped the cosmic web of galaxies. We've delved into the mysteries of black holes. But some questions remain unanswered. Questions about the nature of dark matter and dark energy. Questions about whether we're alone in the universe. Questions about the ultimate fate of everything. We've touched on dark matter many times in this documentary, but let's take a closer look at what it is and why it's one of the biggest mysteries in science. Dark matter is a form of matter that doesn't emit, absorb, or reflect light. We can't see it. We can't detect it directly, but we know it exists because of its gravitational effects. Galaxies rotate in ways that can't be explained by visible matter alone. Galaxy clusters bend light from objects behind them more than expected, and the large-scale structure of the universe matches predictions that include dark matter. So what is it? We don't know what dark matter is, but we have candidates. Weakly interacting massive particles, or WIMPs, were the favorite for decades. These are hypothetical particles that interact only through gravity and the weak nuclear force. They should be produced in the early universe in the right abundance to explain dark matter, and they might be detectable. But decades of experiments have found nothing. Other candidates include axions, sterile neutrinos, and primordial black holes. Each has its supporters and critics. The search continues, and the stakes couldn't be higher. If we can identify dark matter, we'll have answered one of the most fundamental questions in science. Dark energy is even more mysterious than dark matter. It's not matter at all. It's a property of space itself, and it causes the expansion of the universe to accelerate. Dark energy makes up about 68% of the universe. Dark matter makes up about 27%. Normal matter, everything you've ever seen, touched, or experienced, makes up less than 5%. We're a minority in our own universe, and we have almost no idea what dark energy actually is. Are we alone? This is perhaps the most profound question in science and philosophy. In a universe with billions of galaxies and billions of stars per galaxy, it's almost certain that life exists elsewhere. But intelligent life? Technological life? That's a different question. We've been searching for signals from extraterrestrial civilizations for over 60 years. So far, we've found nothing. But the search continues. And with new telescopes like the Square Kilometre Array and the James Webb Space Telescope, we're more likely than ever to find something, if it's out there. One of the most exciting developments in recent years is the discovery of exoplanets. We've confirmed over 5,000 exoplanets, with thousands more candidates waiting to be confirmed. Many of these planets are in the habitable zones of their stars, regions where liquid water could exist. Some are Earth-sized, some are potentially rocky, and some might have atmospheres. The search for a true Earth twin is ongoing. And with future telescopes like the Habitable Worlds Observatory, we might be able to detect biosignatures in the atmospheres of distant planets. Signs of life, if we're looking in the right places. The Fermi paradox asks a simple question. If intelligent life is likely in the universe, why haven't we found evidence of it? There are many proposed solutions. Maybe life is rare. Maybe intelligent life destroys itself. Maybe they're out there but don't want to talk to us. Maybe we're looking for the wrong signals. Or maybe there's something fundamental about the universe that prevents interstellar civilizations from forming or surviving. We don't know. But the silence is deafening. In a universe that should be teeming with life, we seem to be alone. What happens in the end? Every civilization, every star, every galaxy, every atom will eventually die or be destroyed. This is the second law of thermodynamics. Entropy always increases. Over enough time, the universe will reach a state of maximum entropy, a state where everything is uniformly distributed, nothing interesting happens, and no life can exist. This is called the heat death of the universe, and it's the most likely fate of our cosmos. But the heat death isn't certain. There are other possibilities. The universe might stop expanding and contract, leading to a big crunch, where everything collapses back into a singularity. Then maybe the cycle repeats. A new Big Bang, a new universe. This is the cyclic universe model. Or maybe we're just one universe in an infinite multiverse, with new universes constantly being created. Each with its own fate. Each with its own physical laws. We live in one universe, and its fate is our fate. Over timescales far longer than the age of the universe, even more dramatic things will happen. If the proton decay theory is correct, protons will eventually decay, leaving behind only radiation and leptons. Over 10 to the 40th years, all matter will decay. Over 10 to the 67th years, black holes will evaporate. Over 10 to the 100th years, even the heaviest objects will have decayed. And then, the universe will be dark, cold, empty, a void in which nothing ever happens again. This is the long dark, and it's the ultimate fate of everything we know. Here's a strange fact. The universe seems fine-tuned for life. If any of the fundamental constants were slightly different, stars like our sun wouldn't exist. Atoms wouldn't form. The complexity that leads to life would be impossible. Some people argue that this fine-tuning suggests the existence of a creator. Others argue that there's nothing surprising. In a multiverse, some universes will be fine-tuned for life, and we happen to live in one of them. This is the weak anthropic principle. We exist, so the universe must be compatible with existence. But this doesn't explain why the universe is the way it is. It just observes that it is. Another strange idea is the simulation hypothesis. If advanced civilizations can create highly realistic simulations of conscious beings, then maybe we're in a simulation ourselves. Maybe our entire universe is computed by some advanced beings in a higher-level universe. This idea has been explored in philosophy and science fiction. But is it testable? Some physicists have proposed ways to test the simulation hypothesis. If we're in a simulation, there might be glitches, or the laws of physics might have a grainy, pixelated structure at the smallest scales. So far, we haven't found any such evidence, but the search continues. What is the purpose of the universe? This is a question that science can't answer. Science describes how the universe works. It doesn't tell us why it exists or why we should care. These are questions for philosophy, religion, and personal belief. Some believe the universe was created by God for a purpose. Others believe the universe is inherently meaningless and that we must create our own purpose. And some believe the question of purpose is itself misguided. The universe simply is, and that's enough. We've taken a journey through space and time. From the first moments of creation to the ultimate fate of everything we know. We've explored the life and death of stars. We've mapped the cosmic web of galaxies. We've delved into the mysteries of black holes. We've confronted the dark matter and dark energy that dominate our universe. We've asked the questions that philosophers and scientists have been asking for millennia. Where did everything come from? What are we made of? Are we alone? What happens in the end? We don't have all the answers. We may never have all the answers, but we've come further than anyone could have imagined. Here's Earth, a tiny mote of dust in the cosmic void. Our entire history has played out on this pale blue dot. Every war, every peace, every love story, every scientific discovery, everything that ever mattered to us happened on this one planet, orbiting one star, in one galaxy among billions. It's humbling, and it's inspiring. In a universe that doesn't care about us, we've managed to understand the universe to an incredible degree. We've discovered the Big Bang, we've found black holes, we've detected gravitational waves, we've mapped the cosmic web, we've sent robots to Mars and probes to the edge of the solar system. Our journey is just beginning. Earth won't last forever. The sun will die. And if we want humanity to survive, we need to become a multiplanetary species. We're working on it. SpaceX is developing starships that could take us to Mars. NASA's Artemis program is returning humans to the moon. And private companies and governments around the world are investing in space exploration like never before. The future of humanity is in space. It's our only escape from the eventual death of our sun, and it's the next great adventure. The universe is vast beyond imagination. It contains more stars than grains of sand on all the beaches on Earth. It contains more galaxies than we've ever counted. It's been evolving for 13.8 billion years, and it will continue for trillions more. In this vastness, we're insignificant, a tiny species on a tiny planet, orbiting a tiny star, in a tiny galaxy, in an infinite cosmos. But we've managed to understand this cosmos. We've discovered its laws. We've traced its history. We've glimpsed its future. That in itself is remarkable. That in itself is something to celebrate. So where did everything come from? We don't know for certain. But we have a theory. The Big Bang, backed by more evidence than almost any theory in science. How did we get here? Through billions of years of cosmic evolution. Through the birth and death of stars. Through the formation of galaxies and the growth of structure. Through the evolution of life on one small planet in one unremarkable galaxy. Where are we going? Into the long dark, but not yet. Not for trillions of years. We have right now, and that's what matters. So the next time you look up at the night sky, remember this. You're looking at the universe. You're looking at the product of 13.8 billion years of cosmic evolution. You're looking at the same universe that Carl Sagan called home. The same universe that made you. The same universe that will outlive you and your entire species. It's beautiful. It's terrifying. It's mysterious beyond comprehension. And you're part of it. That's not nothing. That's everything. This is Focusmint. Thank you for watching. Remember, the universe is vast. The questions are profound, and the journey is just beginning. Keep looking up. Keep asking questions. Keep exploring, because that's what we do. That's who we are. We are the universe's way of knowing itself.